Hello friends, I welcome you in lecture number 31 on logic. In this lecture we will discuss two problems on writing statements in symbolic form using quantifiers. We have discussed this type of problems in earlier lecture also, and now we are familiar with two quantifiers. One is universal quantifier and another is existential quantifier. So using these quantifiers and some logical operators or connectives, we are able to write down given statement in symbolic form. So we start with this example. This was asked in GTU Summer 2020 exam. First we read what is given. For the universe of integers, that is domain is given to be set of integers. Let px, qx, sx and tx be the following statements. So these statements are denoted by these symbols. X is greater than 0 is denoted by p of x. Q of x denotes the statement x is even. Sx is for x is divisible by 4 and tx denotes that x is divisible by 5. And using this we have to write the given statements in symbolic form. First one is at least one integer is even. So here qx denote that x is an even integer and our domain is the set of integers. And here our statement is at least one integer is even, or equivalently we can write that there exists some x which is even. There exists an x or some x which is even. So whenever we have this type of situation that some property is true for some elements in the domain, then we are using existential quantifier. So for this there exists, we will write this existential quantifier. Here we will write x, and x is even is denoted by qx. So here I will write qx, or we can use brackets also. Some authors are writing these things in the brackets. There exists x such that q of x in the bracket. Second is there exists a positive integer that is even. So here also we have to use existential quantifier, because here we have some integer which is positive and even. So I will write there exists x such that that integer is positive as well as even. So this denotes that x is positive, that is we have to write px, and x is even also. So here we have to use AND operator, and x is even is denoted by qx. Px and qx, this means x is positive as well as even. So whenever we have this type of property that some statements are true for some x, so here we have this statement that there is some x which is satisfying these two statements. X is positive as well as x is even. So in that case we have to use conjunction operator, or we will join these two by AND operator. So px and qx means px is true, that is x is positive. Qx is true, that means x is even. And this is not true for all x. Here they have mentioned that there exists a positive integer that is even. That means we can use existential quantifier. If something is true for some objects or for some x, then we will use existential quantifier. And if our property is given for all the elements in the given domain, then we will use existential quantifier. And if some object is satisfying both properties or more than one properties, then we will use AND operator, and we will join the statements representing those two properties by AND operator. Next statement is if x is even, then x is not divisible by 5. So here this means that for any x which is even, x cannot be divisible by 5. This we can write equivalently in this form also, that for all x in this set of integers which is domain, if x is even, then x is not divisible by 5. For all x in the set of integers, if x is even, then x is not divisible by 5. So now this is true for every x in the set of integers. Therefore we will use existential quantifier for all x. Here we will write for all x, and here we have conditional statement, that is if x is even, then x is not divisible by 5. X is even is represented by qx, and here x is divisible by 5 is denoted by tx. Therefore x is not divisible by 5 will be negation of tx. So here we have negation of tx. So whenever x is even, then x is not divisible by 5, that is x is even implies x is not divisible by 5, that is negation of tx. So this is the symbolic form for this statement for all x. If x is even, then x is not divisible by 5. Next statement is no even integer is divisible by 5. So if you observe carefully, this means that if x is even integer, then x cannot be divisible by 5. So this statement number 4 is nothing but another form or equivalent form of statement number 3. Statement number 3 says that if x is even, then x is not divisible by 5. That same statement we can rewrite in this form also, that no even integer is divisible by 5. That means if x is integer which is even, then x is not divisible by 5. So here also we have this symbolic form, qx implies negation of tx. So you must be able to understand that we can write this same statement in different forms and all are equivalent. Therefore 3 and 4 have the same symbolic form. Next statement is there exists an even integer which is divisible by 5. So this indicates that this is clearly existential quantifier indication. We have to use existential quantifier. There exists an even integer that is divisible by 5. That means there exists at least one x such that x is even, that is qx is true, and x is divisible by 5, that is tx is true. So here I have to use again AND operator, qx and tx, that is both statements are correct. Qx means x is even and tx means x is divisible by 5, and that is true for at least one x, or there exists some x such that qx and tx, qx means x is even, tx means x is divisible by 5. So in this way we can easily write down given symbolic form, given statement in symbolic form. All we have to remember is that whenever some property is given for all the objects or elements in the given domain, we will use universal quantifier, and if property is satisfied for at least one element or for some elements in the given domain, then we will use existential quantifier. And whenever we have universal quantifier situation, then in that case majority of statements are conditional, that for all x, if statement A is true, then statement B is also true. And whenever we have this situation, then here we have that if some objects which satisfy statement A will satisfy statement B also. That is, here we have AND type situation. This is not true for all x, but there exists some x such that A and B are true. So you have observed that in the case of existential quantifier we have used conjunction operator, and in the case of universal quantifier we are using this conditional statement, or we are using these implications. We consider another example. Suppose Px denote that x is a professor, Qx denote that x is ignorant, and Rx is the notation for x is vain. And using these notations we have to write given statements in symbolic form, and universe of discourse or domain consists of all people. So in the domain we consider all the people. First statement is no professors are ignorant. That means whenever some people out of this set, if someone is professor, then he or she cannot be ignorant. So in other words, we can rewrite this statement in this way. For all x in the given domain, we can say that if x is a professor, then x is not ignorant. This is the similar statement for the given statement. No professors are ignorant. That means whenever x is a professor, then x is not ignorant, and that is true for all x, because here they have given that no professors are ignorant. So now whenever we have for all x, we will use universal quantifier, and here we have conditional statement. If x is a professor, x is not ignorant, or in other words, x is a professor implies x is not ignorant. Now x is a professor is represented by px, so here we will write px, and that implies x is not ignorant. X is ignorant is denoted by qx, therefore negation of qx will represent that x is not ignorant. So here we will write implies negation of qx. So in this way we can easily write down given statement in symbolic form. Second is all ignorant people are vain. So this also we can write in this way. For all x in this set of people, if x is ignorant, then x is vain. We have written the same statement in another form. All ignorant people are vain. That means whenever x is ignorant, x is even. So here also we will use universal quantifier. For all x, x is ignorant is denoted by qx, and x is vain is denoted by rx. So qx implies rx. X is ignorant implies x is vain. So here I will write qx implies rx. This represents that all ignorant people are vain, or for all x, whenever x is ignorant, then x is vain. Next one is no professors are vain. So what is meaning of this? Whenever x is a professor, x is not vain, and here it is given that no professors are vain. That means for all x in the set of all people, if x is a professor, for all x, if x is a professor, then x is not vain. And whenever we have for all x, we will use this universal quantifier. X is a professor, that is represented by px. X is vain is represented by rx. Therefore negation of rx is x is not vain. Okay, we can check here. Rx represent that x is Vane, therefore negation of Rx means x is not Vane, and Px is x is a professor. So that I have written here, for all x, whenever x is a professor implies that x is not Vane. So sometimes they ask you to write down given statements in symbolic form, and you can use quantifiers if required, and you can use connectives also and implications, and using all this you are able to write down given statements in symbolic form. So this is all about this session. I hope you like it. Thanks for watching.